Hello, this is Andy Schweitzer. Quick little introduction to gases. Why is a gas a gas? We've already talked about solids and liquids, and we go about sort of saying, okay, there are some internal factors, and there are some external factors. As far as internal factors go, and I'm going to sort of flip to a new page here and look at some internal factors here. Internal factors are, on an atomic, okay, or on a molecular level. What are some things going on here? Well, there's two different types of things we have here. We have what's called an ideal gas, and we have what's called a non-ideal gas. Now, as far as the ideal gas is concerned, this is the most common thing we'll deal with, and a non-ideal gas is simply going to be only in discussion right now, and that's probably about all we'll deal with. It's just there, but we don't really deal with it. Okay. Now, with an ideal gas versus a non-ideal gas, what we have here essentially is gases, okay, particles that are traveling very fast, okay, depending on temperature, they're traveling very fast. They are very far apart, okay, relative to size. Their collisions are elastic. There are no attractions or repulsions, okay, between particles. Now, I would say that this last one is due to these two guys right here. They're traveling very, very fast, and they are very far apart. So essentially, when we go ahead and look at some of the variables involved, because there are no attractions or repulsions between particles, there really is no, the particle is just a particle. It doesn't matter what it is. Okay. Now, a non-ideal gas is one where, for some reason, these particles, okay, if you were to have a, let's say a balloon, okay, right there's my balloon, I have some particles in here, or it could be more likely in a compressed container. As these particles bounce off walls, hit each other, bounce off, okay, for some reason they are close enough, they're closer than they usually are, and they're slower than they normally are. So we have an opportunity here for Coulombic attractions. Okay. Now, some gases, for example, if you have a gas particle in here, so this guy here, if it happens to have some charged particles on it, some charges on it, then there's a chance it might actually be attracted to other charged particles as well. Given the opportunity to slow down and get closer and closer and closer, because Coulomb's law is force equals charge of positive, charge of negative divided by distance squared. If we could somehow get this into a smaller area and get these particles ever so closer together, then there's a chance that these two particles might have an interaction, and at that point maybe they chemically react, maybe they chemically just form a liquid or whatever. Okay, but what is unique about this is some particles don't have any attraction, any charged particles. It'd just be neutrally zero. So the identity of the particle, that is extremely important. I mean, the individual properties of the individual atoms is extremely important. unlike up here, okay, lots of variables are important. What's not important is the actual type of particle. Does not matter. Okay, we don't care. So as far as variables here, okay, now external variables, few more things we can adjust here. One is, of course, temperature. We have pressure. Okay, now with gases, unique to gases, unlike solids and liquids, they can be compressed. So the volume is something we can control. And frankly, just the number of particles makes a difference. Usually this would be listed as N, which would be the moles of gas. So if you blow more air into a balloon, it gets bigger. Volume can be any number of units, which is going to be L for liters usually. Pressure can be either in atmospheres or millimeters of Hg, and temperature generally is going to be in Kelvin. Okay? So these are the external factors. Now, you should understand what these external factors do. Okay, so you should understand just conceptually around your life what happens when these things react to these, gases interact with these variables: temperature, pressure, volume, and number of particles. Now, when we look at instances of these variables, we have sort of a breakdown of two different types of problems. One problem which would be in a rigid container, all right, and another one which would be, let's say, in a balloon, where the container, the volume is allowed to expand and contract. Okay. Now, in a rigid container, the volume is constant. Okay. In a balloon, may sound strange, but the pressure on the inside of the balloon is equal to the pressure on the outside of the balloon, inside versus outside. And that's true because if the inside pressure was bigger, it would expand until the two are equal. So the pressure is constant in this particular situation. Okay. So you should understand that, for example, if I were to, in a rigid container, which might just be in a jar or whatever, if I increase my temperature, I increase the rate at which particles are flying around inside this container. The volume cannot expand, so therefore my pressure increases. At this point, I'm not going to really deal much with number of particles. Okay, we obviously would hope that you understand that you add more particles to it, you get more collisions inside this thing, therefore you get more pressure. Pressure is defined as force per area, and force is legitimately created by collisions. So it's collisions per area is another way of looking at this. So if I crank up my temperature, I have more collisions per area, so more pressure. Add more particles in, I get more collisions per area. So the pressure is legitimately just collisions per area. On the bottom here, you should note that the pressure is constant, so if I increase my temperature, particles move faster, 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 bouncing off the walls, creating temporarily an increased pressure. The volume can expand, so the volume expands, increasing the volume, therefore increasing the area, and I'll end up with the same. Again, here, as you increase temperature, you increase the number of collisions per area, and since that increases the pressure, the balloon expands because the pressures are no longer equal. It expands the volume, cranking up the area till eventually, once again, come to a new equilibrium where the pressure inside equals the pressure outside. So in the end, we will have equal pressures. Okay. In the end, that's just my factors in affecting gases, internal and external.